discuss uh, some of the important topics of distributed system, and those topics are your agreement, protocols, and Byzantine general problem for having consensus. Okay, so these are very important topic in the context of your distributed system. So let us see what exactly these things are. So first we are going to discuss the problem of distributed consensus. So in a distributed system, since we have got number of nodes, number of systems, so there is a need of coordination and communication among all those systems, right? So there may be some number of tasks which may want to execute, so maybe collectively or individually, but there will be some sort of intercommunication, right? So for a certain number of tasks, we may want to have the consensus among our peers. So now we are going to see that how exactly we are going to establish a consensus in a distributed system. So typically this problem is known by a number of other names. We're talking about distributed consensus. So many times we also call it as a reliable multicast. Many times we call it as a Byzantine general problem. We also call it as a interactive agreement, and it is also named as atomic broadcast. So all these problems are same. Okay, so more or less they are known by these number of names. So this has resulted in a voluminous literature which unfortunately is not distinguished for its coherence, and the difference in notation and the haphazard nature of the assumptions obfuscates the close relationship among these problems. So what this person is trying to say that in the literature these things have been addressed differently, these things have been denoted differently with different names, but the core thing is going to remain the same. Okay, so let us see what exactly this problem is. But before moving further, again we need to constitute a model. So let's say our distributed system is composed of n number of processes, right? Then we are also assuming that a process executes a sequence of events and it has local computation. So it may be sending a message M, and then it may also receive a message M. And how do we define a distributed algorithm? We can say a distributed algorithm is an algorithm that runs on more than one process, right? So this is how in an abstract way we can define a distributed algorithm. So these are some of the properties, some of the desirable properties of distributed algorithm. The first one is safety, means that some particular bad things never happens, right? And liveness means it indicates that some particular good things will eventually happen. So these things we have already discussed while studying your mutual exclusive algorithm. So these are the same. Safety means if we are going with a distributed algorithm run, then all the things must go inside the algorithm and then must correctly come outside the or out of the algorithm. So this is what we mean by safety. Liveness means if we are applying that algorithm, then at the end of the algorithm everything should be okay, or while executing the algorithm again the things should be okay. So this is what we mean by liveness. And thereafter, timing and failure assumptions. So it means that it affects how we reason about these properties and what we can prove. So we'll discuss these things about these particular assumptions, which is your timing and failure. So if we are going for the timing, so it may be of two types. It may be synchronous and it may be asynchronous. Then again, there may be a number of failures, or there may be types of failure. So it is up to us that which type of failure we are going to consider in a particular problem. So these are some of the properties, some of the desirable properties indeed in distributed algorithm. Then if you talk about the timing model, then it talks about the specific assumptions regarding the delays between the processes. So execution steps of a correct process, then send and receipt of a message sent between the correct process. And there are many varieties of it, and we are very much interested in two specific varieties of it, and those are asynchronous and synchronous. So asynchronous means we are talking about, or we are not having any assumptions about the messages and the execution delays, except that they are finite. Okay, so messages are going to be delivered in a finite time, but we do not have anything regarding the delay. Okay, means how much delay it is going to incur. Apart from that, if we keep some time bounds on messages delivery or their execution, then we can say that we are talking about the synchronous time. Okay, so uh, asynchronous is a your superset and synchronous is a subset. So if we put up some time bounds, then we can say that we're talking about the synchronous time. Okay, otherwise with no assumptions, of course we'll be going for the asynchronous. So it depends upon the timing. If you are imposing the timing, then it means we are talking about synchronous. If you're not imposing any timing, then we are talking about the asynchronous, right? Then these are the some of the differences between the synchronous and asynchronous. So this is how you can say that the processes share a clock in synchronous, while in case of asynchronous, processes operate asynchronously from one another. In synchronous, we do carry some timestamps in between the processes, while in asynchronous, no claims can be made about whether another process is running slowly or has failed. So there will be no claim at all. Okay, since we are not caring about the timings and all. And in case of synchronous, the communication can be guaranteed to occur. Okay, while in case of your asynchronous, there is no time bound. Okay, on how long it takes for a message to be delivered. So if the things are getting delivered within the specified time, that means it is a synchronous one. And if the things are having no time bound, then you can say that we're talking about the asynchronous. Okay, then the failure model. So when can we say that a process has been failed or a process is a faulty? So we can say a process that behaves according to its input output specification throughout its execution, then that particular process can be termed as the correct one. Okay, and a process that deviates from its specification, so whatever specification we have assigned to it initially, if that process is not performing as per that specification, then we can say that that particular process is a faulty one. And again, there can be many variety of faulty processes. So especially we are very much interested in the two types. The first one is Byzantine failures or Byzantine faults, and the other one is fail stop failure or the fail stop fault. So again, and this is the, so in case of Byzantine failures, so we do not have any assumptions about the behavior of a faulty process. It can be of any type. Okay, suppose if two processes are there and they are communicating to each other, so it may possible that it has failed to send a message, or the process which was responsible has been altered prematurely. Then it may possible that the message has been sent and then it has been lost somewhere in between the or in the communication channel, right? Or it has been failed in the buffer of the receiving process. So there will be number of failures. So we do not make any assumption, or we do not know anything then we can categorize that sort of failure under the Byzantine failure. Okay. And if we talk about its execution time specifically, so if a process halts its execution prematurely, then you can say that it is a type of fail stop failure. Okay. Then errors as failure assumptions. So specific types of errors are listed as failure assumptions. For example, the communication link may lose a message, right? Or it may possible that the message has been sent many times, or uh, the messages which were supposed to maintain a particular order, that order has not been maintained. Okay, so this is also considered as one of the failure. And then it may possible that many process may die and then again they may restart it. So this sort of things may happen. And then in fail stop failure, a failure result in the process P. Stopping also referred to as a crash failure. So if the process is stopping, then again it is a type of the failure, and we can categorize it as a crash failure. And if P works correctly until the point of failure, so it is a crash failure in short. And in fail stop failure, of course, the P doesn't send any more message since it has got failed. Apart from that, P doesn't perform actions when the messages are sent to it since it has got failed. And other processes can detect that a particular process has failed, about which we were talking about. So these are the things which are ought to happen when we talk about a failure in process P. Then the failures can be detected by a few methods. So we are going to discuss one of the method. So in order to detect a failure, we can use some failure detector. So when can we say that a failure detector is a perfect one? So we can say that a failure detector is a perfect one when it is producing no false positives, and whenever there is a failure, it is eventually reporting those failures. So if these two things are there, then we can say that it is a type of a perfect failure detector. Okay. Then we can have one algorithm called as a heartbeat protocol, or the heartbeat algorithm, through which we can identify whether a particular process is working or not, or whether a process has failed or not. So in this is a very primitive one. So it assumes partially synchronous environment. That means again some notion of time bound will be there. So if a process sends I am alive message to all the other processes regularly, then we can say that that particular process is alive, whoever is sending this particular message, right? So if process I doesn't hear from process J in some time t, where we are considering the transmission time, and then we are giving some extra time for the process. So if the process J is unable to respond within this time, then we can say that the process J has failed. Okay. So depends upon the T delivery being known and accurate. So we are considering the transmission time and the processing time at the process. Okay, so we are including both the times together, then we are creating a time bound. So if a process is responding within that time bound, then we can say that that process is working. And if it has failed to respond, then we can say that process has got failed. So every time all those processes will be sending a heartbeat message, I am alive. And if any process observe that some of the processes has not sent this message, then it will infer that those processes have got failed, or something wrong has been happened with those processes. Okay, so this is a very simple protocol. Then other failure models can be omission failure, timing failure, response failure. So in omission, process fails to send a message or receive a incoming message. In case of timing failure, the process is failed to respond in a specific specified time interval. And in case of response failure, the value of the response is incorrect. Okay, so whatever response it was supposed to send, that response is not up to the mark, so it will be considered as a response failure. Now here comes the Byzantine failure. So in this case, a process may fail in the variety of ways which are totally unknown, and here the P can be modeled as malevolent entity. That means it can send the messages and perform the actions that will have the worst impact on the other processes. And it may possible that it may collaborate with the other failed processes, and it may create uh, uh, something more wrong to the overall system. Okay. Then the setup of distributed consensus. So just a minute. In this particular setup, first of all, we need to have n number of processes, and they need to agree on a single value. Okay, and each process begins with a value. So whenever we have got a system, and in that system we want to have a consensus, so initially all the processes will propose some value. Okay, so this is what we mean by this point. And in the first one, the example application of consensus may be performing a commit in a replicated or distributed database, and maybe collecting multiple sensor readings and deciding on an action. So we may have to come at the last on a single value. So the second point has been covered. Then in the third one, each process can irrevocably decide on a value. So at the end of the algorithm, all the processes has to converge on a single value. And if we have got n number of processes with f number of faults, then we can say this many number of faults are allowed. Okay, so in a system, f must have to be less than the number of processes. Only then we can have the consensus, otherwise not. Or in short, this should be the minimum condition, where the total number of faults are less than the total number of processes. Okay, and there may be one question, where how do we reach consensus if there are no failures? So there are no failures means there are no changes to the inputs. So all the processes are going to receive the same inputs. So for example, if we have got n number of processes, so let's say in this case we got three processes. So inputs which are going to pass to all these processes P1, P2 and P3 are going to be same, right? And the functions which will be running over here, okay, that would be same. And since all these functions are same, inputs are same, and the process behavior is same, so they are also going to create a common value. So there will be a consensus reached very easily. Okay. So the properties of distributed consensus are the agreement, since all the processes are going to agree on a common value, and then the validity. So whatever value has been proposed, that will be carried by all the processes, and then the termination. So in case if all the processes has decided some value, then after deciding that value, the overall process will get terminated. So these 3 points are going to define your safety and liveness property. Fine. Then this is one of the algorithm called a synchronous fail stop consensus algorithm. You can also call it as a protocol. And this is the name of the algorithm, FloodSet. And in this algorithm, we have got a set of values, we call it as a S, and then we can have a decide function, and this decide function can be minimum, maximum, majority, or any other default function. So we'll see in detail how exactly this FloodSet algorithm works and how exactly this pseudocode is working. So it assumes that the nodes are connected and links do not fail. Okay, however, the process may fail. So this is the example of that FloodSet algorithm. So let us say we have got three systems or three processes S1, S2, and S3. So initially they were having the values 0, 1, and 1. So these are the initially proposed values to have the consensus. Okay. Then S1 has sent some values to S2 and S3. So the value has reached the S3, but the communication which S1 was trying to establish with S2 has got failed in between. Okay. Then similarly, S2 has tried to communicate with S1 and S3. So eventually, S2 has succeeded uh, to communicate with S3, and S3 has also succeeded to communicate with S2. But S3 has failed to communicate with S1, and similarly, S2 has also failed to communicate with S1 because the S1 thereafter has got failed after sending the message. Okay. So at the end of this run, S2 will be having the value 1. Okay, because it was having the value 1 initially, and the value received from S3 was also 1. So 1 comma 1 means 1. So at the end, we are going to find out the union. Okay, union of the values. And similarly, at S3, it was proposing the initial value 1, and then it has received 0 from S1. So after evaluating the union, it will be having 0 comma 1 at the end of the run. So this is the end of round 1, right? And then in the second, again S2 and S3 exchanges the messages, and after this exchange, they will come up with these values. So this time 0 comma 1 will be sent to S2 and 1 will be sent to S3. So when the union will be taken, this will be the final values 0 comma 1, 0 comma 1. So at the end of round 2, we can say that if the desired function is the minimum function, that means if we take the minimum of these two values, which is 0, so 0 can be the final value on which the consensus can be established. Okay, and if in case we are going for the maximum function, in that case it is going to be 1. So it is up to us that what desired function we are going to use in the consensus algorithm. Okay, so I hope you would have got the idea of FloodSet algorithm. Any problem, any doubt, students?
Yes, sir.
Okay. So if you have got f number of failures, then it is going to require f plus 1 number of rounds. And again, in order to have the agreement, this many number of rounds will be required. And then we have to decide or we have to see that what function we are going to use to have the consensus. And again, the validity, so it will decide results in a proposed value. So at the end, whatever value will be chosen, it will be going to be there for the rest of the execution. And termination, so after a plus 1 number of rounds, the algorithm is going to be terminated. Now we are going to discuss a very important consensus algorithm called as a Byzantine consensus algorithm. So Again, we are going to assume few things, and one of the major assumption is all loyal generals decide on the same plan of action. So we are talking about military or a defense example where we have got some personals, and few personals are lieutenants and few persons are the generals. Okay, so as we know, in that typical structure where we have generals, okay, and we have lieutenants. So generals are the superior officers than the lieutenants, right? So all the lieutenants are supposed to obey their generals. So this is a hierarchy in our army, in our defense system. So in the number of scenario, they need to plan for their actions, and in that case this person who is a general is responsible to make a plan, and then that plan will be passed to its descendants, which are lieutenant in this case, right? So now they need to follow their generals, but now we are going to see if something wrong happens with the general, or if something wrong happens with the lieutenants, then what would happen? So what has been done over here, we have, or the you can say that this master node and this slave node, or the master process or the client process, has been made in a generals and lieutenants communication of the uh, defense problem. Okay, so let us see how exactly the things are going to happen. So a typical inter-process communication problem where we may have some process faulty has been mapped to this problem. Okay, so we are going to see how faulty processes are going to be handled with the help of this analogy. So as discussed, all loyal generals decides on some plan of action, right? Apart from that, it implies that all loyal generals obtain the same information, and a small number of traitors cannot cause the loyal generals to adopt a bad plan. So we are assuming that some bad traitors are there, or in other way, you can say that we are assuming that some of the processes may get crash or may get failed. Okay, so decide function in this case is going to be the majority. Okay, so we are going to have one more thing called as a default action, and in this case, if the consensus is not deriving or not being derived, then we can say we can consider retreat as a option. So let us see what happens in this case. So in Byzantine model or synchronous Byzantine model, there is no algorithm to solve consensus if only oral messages are used. Oral messages means they can be changed. Okay, unless more than 2/3 of the generals are loyal. So this is the condition, and it says that we cannot solve consensus if the oral messages are being used and more than 2/3 of the generals are loyal. Okay, in other words, impossible, it is very much impossible if n is less than or equal to 3f, where n is the total number of processes and f is the number of faulty processes. Okay, so this condition should be false if we want to have a consensus. Fine. So oral messages means the sender can alter a message that it received before forwarding it. Fine. So all the things are pretty much straightforward, but there is a very interesting thing when we discuss a special case where n is equals to 3 and f is equals to 1. That means total number of processes are 3 and number of faulty process is 1. So in this case, 3 will be less than equals to 3 into 1, right? So let us see what happens in this case. So the overall scenario has been divided into 3 number of cases. So in the first case, traitor lieutenant tries to foil the consensus by refusing to participate. Okay, so these white heads persons are the loyal ones or the good ones. Okay, and these black head guys are the bad guy or the bad person or the traitor. So the person who is sitting up in the hierarchy is the general, commanding general, and the persons who are sitting down the hierarchy are the lieutenants. So in the first round, commanding general sends a message to retreat. Okay, they are going for a war, and then they need to decide that what to do with the enemy, whether we are going to attack him or whether we are going to retreat. So there are two situations only. So in the round one, commanding general is sending a message rated on the basis of these situations. Fine. Then the first round, commanding general has sent retreat and retreat to lieutenant 2 and lieutenant 3. Means to both the lieutenant, it has sent a message to retreat, right? Then in round 2, L3 sends retreat to L2, but L2 sends nothing. Okay. In this case, L3 is sending a message to L2. Fine. But in this case, your L2 is not responding. So in this case, what will happen? L3 is going to decide to retreat since his commanding general is saying to retreat. So there is no problem in the case 1 since the commanding general is saying for the retreat and he is not getting any response from the L2. So in this case, it will go, or the general will go with the orders of his commanding general, and therefore it will decide to retreat. Fine. So there is no problem in case 1. So here the loyal lieutenant obeys the commander. That means the consensus has been established. Fine. Now let us see the second case, and again there can be two scenarios in the second case. So we are going to discuss the first case. So in the first case, the traitor lieutenant tries to foil consensus by lying about the order sent by the general. So in this case again, the lieutenant sending the order of retreating to L2 and L3, right? Then this time L3 sends retreat to L2 and L2 sends attack to L3. So you can see that it is sending the exact instructions which he has received from the commanding general. But since this is a faulty one, so it is trying to foil the party by changing the message. So this time, this faulty process, so the traitor is sending the message after iteration. So he is sending attack. So this time your L3 is again going to decide for retreat. Since he is getting the message of retreat from the commanding general and then getting a message to attack from the lieutenant 2. So it has to decide in between attack and retreat, since the retreat is being received from the commanding general and the default option is also retreat. So in this case, the lieutenant 3 is again going to obey the commanding general. So again, you can say that somehow the consensus has been established. Fine, no issue. Now let us see uh, the second case, in case 2. In this case, again, commanding general is sending some message, but this time it is sending a message to attack. Earlier it was sending message to retreat. So attack message has been sent to L2 and L3. Then L3 sends attack to L2 and L2 sends retreat to L3. Okay. And now this time attack is being received from the commanding general and retreat is being received from the L2. So again, there is a difference in opinion, right? So since this is a very sensible, or you can say very critical option, so in this case, it will be again having a drop, or you can say not having the clear consensus. So again, it may take the help of that default option, which is retreat. So in this case, this L3 will decide to retreat. So with this, you can say that the loyal lieutenant disobeys the commander, which is bad, and hence you can say that the consensus is being violated. Okay, so consensus is not being achieved fully.
Hello,
Right?
sir.
Yes,
Sir, it is necessary for Lieutenant 3 to ask suggestions about Lieutenant 2. Can't
yes.
he just follow the orders of Commanding General?
Actually, we are just trying to create an analogy where we are expecting that each process do communicate with each other. It may possible that one of the process may get failed where it is unable to reply. But in some process, it may possible that the processes are replying with some other values. Okay, so how to deal with those situations? And when in this case, we are going to discuss with the help of this Byzantine general problem analogy. Am I clear?
Okay, sir.
Okay, so we are assuming that all the processes are participating in order to achieve the consensus, and it is not advisable that the failed process uh, are not contesting in achieving the consensus. So we are allowing the faulty processes as well in the process of consensus. Okay, so this problem is being addressed. Clear?
Yes, sir. Yes, sir.
Then there can be a third case. So in this case, earlier the lieutenant was a traitor, but in this case, the commanding general is a traitor. So in the first round, commanding general sends attack to L2 and retreat to L3. So it is sending attack to L2 and retreat to L3. Okay. Then L3 will send retreat to L2 and L2 will send attack to L3. Right. So both will be having the different opinions. Right. L2 will be having that the attack is being received from the commanding general and retreat is being received from the L3. And similarly at L3, it is receiving retreat from the commanding general and attack from the lieutenant 2 or L2. So again, there will be difference of opinion and there will be no clear consensus. And it is totally uh, totally depend upon the assumptions whether we are going for the default value or not. And the default value which were considered in the case 1 and case 2 was retreat. Okay, and it is not advisable to go for the default values. And if we are going for default values, you can say that we are violating the consensus because we do not have any clear-cut consensus. That is why we are going for default values, right? So even in this case, the values which are there with the L2 are a comma r and r comma a. So you can say that no clear consensus are there. So it may decide to retreat and it may decide to attack, or it may also decide to retreat. So there is no clear consensus. So at the end, we can say if this is the case, which is if this is the case where n is either less than 3f or equal than 3f, then the consensus cannot be achieved. And recently, we have seen a special case where n was equal to 3f. Okay, so n has to be greater than this one. Only then we can have the consensus. Fine. So in connection to this, let us consider one more problem where we have got n equals to 4 and f equals to 1. So in this case, we can say the n is greater than 3f, right? N is 4 and 3 into 1, which is, if you just evaluate this one, then you will find that n is greater, right, than 3f. So again, the same scenario has been considered. One of the lieutenant has been considered as a traitor, right? And a value has been passed from the commander to all the lieutenants. Then the lieutenant who is traitor is sending different values to L3 and L4, and then all the loyal lieutenants are sending the same value. So at the end of the run, L3 will be having these values, L4 will be having these values. Okay, so the decide function in this case has been chosen again as a majority. So the majority in this case is of V, and again in this case is of V. So both can go with a value V. So this is how the consensus has been achieved easily in this case. Fine. And in another scenario where your commanding general is a traitor, so what this can do, this can send the different values to all the lieutenants. Let's say X, Y, Z has been sent to all the lieutenants L2, L3, and L4, and then they have passed these values to the other lieutenants. These are values, right? So over here, since the decide function is in our hand, so all the lieutenants will be having the values L2, L3, and L4. So they can go for any function, for the minimum one, for the maximum one, for the average one, for the majority. Each case, they are going to have the consensus at the end. Okay. So moral of the story is n has to be greater than 3f if a system want to have the consensus. Okay, where f is the number of faulty process. Am I clear, students?
Yes.
Okay. So now we are going to discuss the second topic for today's lecture, that is distributed deadlock detection. So since all of you are already aware regarding what is a deadlock, you would have studied this concept in operating system. So while talking about distributed deadlock detection, again we are going for a number of assumptions. So the assumptions are system has only reusable resources, and then only exclusive are going to be provided to the resources, and only single copy of each resources is there. Thereafter, the state of a process can be in a running mode or a blocked mode. Then the running state can be a process has all the resources, and in a blocked state, a process may be waiting for one or more resources. Okay. In deadlocks, there can be two types of deadlock. The first one is a resource deadlock, and the other one is a communication deadlocks. Resource deadlock, where a process needs multiple resources for an activity, right? And a deadlock occurs if each process in a set requests resources held by another process in the same set, and it must receive all the requested resources to move further. This is a typical definition which we know, right? In case of your communication deadlocks, process wait to communicate with each other in a set where each process in the set is waiting on another process message, and no process in this set initiates until it receives a message for which it is waiting. So in short, a deadlock can be there while a process is waiting for another process, to release all the resources which that process is in the need, right? And typically, how do we detect a deadlock? We detect a deadlock with the help of a WFG graph, wait for graph. And if we talk about the databases, if we're talking about databases, then it will be termed as a transaction wait for graph. So if we are receiving, or if we are able to detect a directed cycle in a graph, then you can say that there is the essence of a deadlock, right? So here you can see that there is something which a process P1 wants, and that is being currently acquired by P2. And similarly, there are some number of resources which P2 wants, and those resources are currently being acquired by P1. Okay, so this is a typical example of forming a cycle, and it means that a deadlock has been detected. So in a graph model, if we talk about wait for graph, so let's suppose we've got two processes, P1 and P2, and P1 is trying to get access to the some set of resources, let's say R1, and these resources are currently being held by P2. Similarly, there are some set of resources, let's say R2, which is currently being acquired by P1. Okay, and P2 is also wanting to have them. So this is a cycle which is being formed, and hence we can deduce that there is a essence of a deadlock. Okay. There can be two types of models in deadlocks called as end models and OR models. So in case of end models, a process or a transaction can simultaneously request for multiple resources. And if it is requesting for multiple resources, then it remains blocked until it has got all the resources. Okay, or all the resources has been granted to it. And in case of OR model, again a process or transaction can request for multiple number of resources, and it remains blocked until at least any one of them has been granted. So this is the basic difference between AND or OR model. Okay, so if all the requested resources are being granted, then you can say it is a typical example of AND model. Or if one of the resources has been granted and still the things are happening smoothly, then you can say that the model which has been assumed in this case is a OR model. Fine. So the sufficient condition to have a deadlock is to detect a cycle, right? So as you can see that a cycle has been detected over here among P1, P2, P3 and P4. So since a cycle is there, then you can say that there is a deadlock. So let us see in AND model, again, we can see that there is a cycle in between P2, P1, P2, P3 and P4. This is P3 and this is P4. Okay, let us say this is P5 and this is your P6. Okay, so there is a cycle in between P1, P2, P3 and P4. And this is a particular example of an AND model. And now we are going to see an example of OR model. So in case of OR model, there is going to be a NOT. So a presence of a NOT will be there in case of OR model. This is a basic difference between AND and OR, despite that definition. So what OR model says that it is impossible to leave the NOT by following the edges of the graph. And what does it mean exactly? So let's say if we are finding a cycle in between P1, P2, P3 and P4, and if we are just going through these cycles or these edges, let's say like this, okay, and still if we are unable to leave the graph, we are not able to leave the graph, still we are in the loop. Okay, so if the thing like this is happening, then you can say that there is a NOT, because we are not able to leave the cycle. In earlier class over here we were able to leave the cycle. Okay, it was not again sending back to the cycle. So a NOT is not there, and over here in our case there is a NOT. Okay, So deadlock prevention is difficult. So most of the cases we do go for the deadlock avoidance. Okay. So in case of deadlock detection, again we need to find the cycles. If the cycle is there, then we can say that there is a deadlock. So the deadlock detection algorithm must satisfy two conditions. The first one is there should not be any case where the present deadlock has not been detected. And second, it must not detect the false deadlock. Right. So these are the basic two requirements of the deadlock detection algorithms. Then there can be three types of deadlock detection algorithms in distributed system. The first one is centralized control, where a control site is responsible to construct the WFG graphs and it checks for the directed cycles. If the cycles are there, that means there is a deadlock. And it maintains WFG graphs continuously, which is built on demand by requesting WFG's graph from the individual sites. Fine. And in case of distributed control, WFG is spread over different sites and any site can initiate the deadlock detection process. While in case of hierarchical control, sites are arranged in a particular hierarchy. So if this is the hierarchy, then only this particular node can construct the WFG for these two. Okay. So what we mean to say that if we want to construct the WFG in between these three, then only this particular or the node, or only the process which is behaving as a root node can only construct the WFG graph. Leaf nodes cannot construct a WFG graph. Okay. So a site checks for cycles only in the descendants only. Now we are going to see one of the algorithm of the centralized type, and that algorithm is your Rammamoorthy two-phase algorithm. In this particular algorithm, each site maintains a status table of all processes initiated at that site. So if you got n number of processes, so any one process can take the job of the central process, and then that process is going to maintain a status table. So in this status table, the details of all the resources which has been logged and all the resources which are being logged will be there. Then in the second step, the controller will request this status table from each site, and it does collect all this status table on a regular interval. And the moment it receives all the tables, it searches for the cycle. Okay, so first the controller will poll for the status table, and the moment the controller side collects the status table from all the client side, then it will search for the cycles. So if there is cycles, or if there is any cycle, then we can say that there is a deadlock, otherwise there is no deadlock, right? And if in case a deadlock has been detected, then it will again request for a status and then construct our WFG based only on the common transactions in the second tables. Okay, so if a deadlock has been detected, then again the status table will be asked, and only the common transactions will be used in order to create the WFG. And if in that second WFG graph, if still a cycle is there, then you can say that there is deadlock. Otherwise, no. So a cycle has to be detected in the two consecutive requests made from the controller side. Okay. And in the later times, it has been proved that the cycles in two consecutive reports need not result in a deadlock, and hence this algorithm detects the failed deadlocks. Okay, so it is not necessary that 2 times a process has to ask the other processes, okay, in order to detect a cycle. So it may possible that in the first time a cycle has been detected, and when the next time it is polling, at that time the cycle has got resolved, okay, or the deadlock has got resolved. So in the later time it doesn't prove that it is not necessary to poll the status table twice, okay, so it may detect the false deadlocks. Okay, so this is the Rammamoorthy two-phase algorithm to detect the distributed deadlocks. Then in the second variation, now each site maintains two status table. The first one is the resource table and the other one is a process table. In resource table, transactions that have logged or are waiting for the resources, the transactions that are or that have logged or are waiting for the resources are being placed, and in the process table, the resources which have been logged by or waited by the transactions are being placed. And in this case, again, the controller periodically collects these tables from each site, and if or after collecting the resource table and the process table, it does create a WFG, okay, from the transactions which are common to both the tables. And if there is no cycle, that means there is no deadlock, and if there is a cycle, then it can be deduced that there is a deadlock. So this is how it works, and this is called as a Rammamoorthy's one-phase algorithm for distributed deadlock detection. So this is what regarding your distributed deadlock. In case if your students have got any doubt, then you can ask. Any doubt, any query?
No, sir.
Okay. Okay, students, then in that case, I'll end the class here only. Thank you.